Hi, my name is Suraj Singh. I am one of the mentors at Programming Pathshala. I am expert on Codeforces and 5-star on Codechef. Today we are going to solve this problem called minimizing coins. So let's try to understand the problem statement first. So problem says that we will be given with n values of coins and we have to produce a sum of money equals to x, right? Using those values of coins in such a way that the number of coins is minimum. For example, if n is equals to 3 and x is equals to 11, and let's say the values of coins are 1, 5 and 7. So we can use coins with value 1, with value 5 or with value 7 to produce a sum of 11, and we have to find out the minimum number of coins that will be required to do so, right? So let's see how we can get a sum of 11 using these coins. So we can pick a coin with value 7 and then we can pick 4 coins with value 1. This adds up to 11, right? Similarly, we can pick 2 coins with value 5 and we can pick 1 coin with value 1, and this also adds up to 11, right? So similarly, we can have more ways to get a sum of 11, but the minimum number of coins that are required to get a sum of 11 will be 3, and that will be this combination: 2 coins with value 5 and 1 coin with value 1, right? So this is what problem is asking us to do. So now what we can do is we can take an example and try to figure out how we can solve or approach this problem, right? Let's take n is equals to 3 and let's say the values of coins are 4, 5 and 7. And let's say we want to produce a sum of 11, right? Okay. So now what we want is we want to find out the minimum number of coins that are required to get a sum of 11 using these 3 values of coins, right? And to get a sum of 11, we will pick some number of coins, right? And while picking a coin, we have 3 options. We can either pick a coin with value 4, or we can pick a coin with value 5, or we can pick a coin with value 7, right? So let's try to explore these 3 possibilities. So we want a sum of 11. The first possibility is that we can get a coin with value 4. In that case, the remaining value will be 7. Because we wanted a sum of 11, we got a coin with value 4, so the remaining value will be 7. Similarly, if we talk about the second possibility, we can get a coin with value 5. In that case, the remaining value will be 6. And the third possibility is that we can get a coin with value 7. In that case, the remaining value will be 4, right? Okay. So now if we focus on the first possibility, then we can say that we wanted a sum of 11. We got a coin with value 4, right? Now we want to find out the minimum number of coins that are required to get a sum of 7. Because once we have the minimum number of coins to get a sum of 7, then we can use all those coins and they will have a sum of 7. And in those coins, we can add one more coin with value 4 and the sum of all these coins will be 11, right? So if we just look at these 3 values, we can say that to get a sum of 7, we just require 1 coin. And because we require only 1 coin to get a sum of 7, we can say that using 2 coins, we will be able to get a sum of 11, right? So that's why we want to find out the minimum number of coins that are required to get a sum of 7, right? Similarly, for second possibility, we need to find out the minimum number of coins that are required to get a sum of 6. And for the third possibility, we need to find out the minimum number of coins that are required to get a sum of 4, right? So let's say now we want to find out the minimum number of coins that are required to get a sum of 7. So for that also we can pick a coin, and again we have 3 possibilities. We can either pick a coin with value 4, 5 or 7. So let's say we pick a coin with value 4. In that case the remaining value will be 3. And if you pick a coin with value 5, in that case the remaining value will be 2. And if you pick a coin with value 7, in that case the remaining value will be 0, right? So if we talk about this 6, then again we have 3 possibilities. We can pick a coin with value 4. In that case the remaining value will be 2. If we pick a coin with value 5, in that case the remaining value will be 1. And if we pick a coin with value 7, then what will happen? See, we wanted a sum of 6, but we got a coin with value 7, so which is greater than what we required. So if we just look at this possibility, then first we took a coin with value 5, then we took a coin with value 7, and the sum of these 2 coins is 12, but we wanted a sum of 11. So now we can say that it is impossible to get a sum of 11 if we already have sum of coins equals to 12, right? Okay. So now we can say that we required a value of 6 and we got 7. So the required value is -1. And because the values of coins is positive, or we can say non-negative, in that case we will never be able to get a sum of -1, right? Okay, cool. So now if we just talk about the last possibility, which is to get a sum of 4, in that case also we have 3 possibilities. We can either pick a coin with value 4, in that case the remaining value will be 0. And if we just talk about the other 2 possibilities, it will be impossible to get a sum of 4, right? So we can skip that. Just like here we are getting a negative requirement. So if we use 5 and 7 to get a sum of 4, then we can say that it will be impossible to get a sum of 4, right? Okay. So if you talk about 3, 2 and 1, using these 3 values of coins, it is impossible to get 3, 2 or 1 as a sum. So we can say it is also impossible and impossible to get this sum, and also this. So it's impossible to get these 5 values of sum, right? Okay. Now if we look at 7, then to get a sum of 7, we had these 3 possibilities, right? And out of these 3 possibilities, 2 of the possibilities require a sum which is impossible to generate using these 3 values of coins, right? We can't generate a sum of 3 or 2. But if we look at the third possibility, then we can say that to get a sum of 0, we require 0 number of coins, right? If we don't pick any coin, then the sum of coins will be 0, right? And now because the minimum number of coins that are required to get a sum of 0 is 0, then we can say to get a sum of 7, we will require at least 1 coin, right? And because we require 1 coin to get a sum of 7, then we can say that we will require 2 coins to get a sum of 11, right? Similarly, if we talk about 6, here we wanted to find out the minimum number of coins that are required to get a sum of 6. And for that we had these 3 possibilities. And all these 3 possibilities, we require a sum which is impossible. We can't generate a sum of 2, 1 or minus 1. That means it is impossible to get a sum of 6 using these 3 values of coins, right? So it is impossible to generate a sum of 6. Okay, now if we just talk about 4, then we can say that for 4 also we had 3 options, but we will not be able to generate a sum of 4 using values 5 and 7. So the remaining possibility is that we use a coin with value 4. In that case, the remaining value will be 0. And to get a sum of 0, we require 0 number of coins, right? And because we require 0 number of coins to get a sum of 0, we can say that we require 1 coin to get a sum of 4. And because we require 1 coin to get a sum of 4, we will require 2 coins to get a sum of 11, right? So out of these 3 possibilities, 2 of them are able to generate a sum of 11, and both of these possibilities require 2 coins, right? So the minimum number of coins to get a sum of 11 is 2, right? Okay. Now we can observe few things. Like to produce a sum of x, we will be having n number of options, right? Because we will be having n values of coins. And while exploring all these options, we can say the problem statement will remain same. For example, here we wanted to find out the minimum number of coins that are required to get a sum of 11. And here we wanted to find out the minimum number of coins that are required to get a sum of 7. So the problem statement is same, only the size is reducing, right? And because the problem statement is same, we will be able to use same function to calculate the answer for both the values, right? And because the size is reducing, so we can write a function which is recursive in nature. Okay. Cool. So now we can try to figure out a recursive relation for this problem. And for recursive relation, we need a function f of x which can return us the minimum number of coins that are required to get a sum of x. So to understand, let's try to take the previous example. Let's say x is equals to 11 and n is equals to 3 and the values of coins are 4, 5 and 7, right? So what we want to do, we want to find out the minimum number of coins that are required to get a sum of 11 using these 3 values of coins, right? That means we need to find out the value of f of 11. And we have already seen that for to get a sum of 11, we have 3 possibilities, or we can say we have 3 options. So if we pick a coin with value 4, in that case we would want to find out the minimum number of coins that are required to get a sum of 7. And if we want to do so, then we can call this same function for f of 7, and this will return us the minimum number of coins that are required to get a sum of 7. Okay. Now for the second possibility, we can pick a coin with value 5. In that case, we would want to find out f of 6, the minimum number of coins required to get a sum of 6. And for the third possibility, we can pick a coin with value 7, and in that case, we would want to find out the value for f of 4, right? Now, can we say that value of f of 7 will be 1? because we only require one coin to get a sum of 7, right? Okay, and it is impossible to get a sum of 6 using these 3 values of coins, right? And according to the problem statement, in that case the answer should be, or the value should be -1, right? And the value for f of 4 will also be 1, because to get a sum of 4 also we require only one coin. Okay, now we know the answer for all these 3 possible cases. Now we need to find out the value for f of 11. So if we want one coin to get a sum of 7, then can we say we will require 2 coins to get a sum of 11, right? Similarly, if we require one coin to get a sum of 4, then we can say we will require 2 coins to get a sum of 11, right? So can we say that f of 11 will be equals to minimum of f of 7 plus 1 comma f of 4 plus 1 plus 1, right? Or we can say minimum of f of 7 comma f of 4 plus 1, right? We are excluding the case where it is impossible to get a sum, right? So except that for all the possibilities we are taking the minimum and we are just adding 1 to it. And why we are adding 1? We are adding 1 because we got all these possibilities after picking a coin, right? So this coin is representing just that coin which we picked, and we got all these possibilities, right? Now if we try to generalize this recursive relation, then we can say that for f of x we will have n number of options. Here n is equals to 3, so we got 3 options, but for a general case we will be having n number of options. So the first option could be to pick the first element, which will be a of 0, right? And if we pick a coin with value a of 0, then we will call this function for x minus a of 0. Why? Because we wanted a sum of x and we got a coin with value a of 0, so the remaining value will be x minus a of 0. Similarly, the second option could be to pick a coin with value a of 1. In that case, we will call x minus a of 1, right? Similarly, we will be having more options, and the last option could be to pick the last element, which is a of n minus 1. In that case, we will call f of x minus a of n minus 1, right? So for a general case, we will be having these n options. Out of these n options, for few of the options, it will be impossible to generate a sum, right? Just like f of 6. And if it is impossible to generate a sum, then we need to exclude that possibility. And for the remaining possibilities, we need to find out the minimum value, right? And then we can just add 1, okay? Now we can say that this recursive relation will be valid for all the values of x greater than 0, right? And if x is equals to 0, in that case we can say the minimum number of coins that are required to get a sum of 0 is 0. So if x is equals to 0, in that case the answer is 0, right? And if x is smaller than 0, in that case it is impossible to get a sum which is negative. So we can say in that case the answer is -1, right? So this is the recursive relation. Now we can try to write a recursive code. Okay. Now let's try to write a function called solve, and we will pass an integer x to this function, and this function needs to return the minimum number of coins that are required to get a sum of x using given n values of coins, right? So the return type of this should be integer, and first we will take care of base cases. In that case we can say if x is equals to 0, we need to return 0. And if x is smaller than 0, in that case we need to return -1, right? Okay. Now if these two conditions are not true, in that case we need to follow this recursive relation. And in this recursive relation we need to make n function calls, right? And to make these n function calls, what we can do is we can run a loop starting from 0 and going till n-1, right? So let's run a loop for int I is equal to 0 to n-1. And what we can do is we can make a call to f of x minus a of I, right? Now this function will return something. It will return the minimum number of coins that are required to get a sum of this value, right? And if it returns -1, in that case we can say that it is impossible to generate sum equals to this value, right? And in that case we can just ignore this function call, or we will not include this function call, right? Otherwise what we will do, otherwise we'll have to take a minimum of this, right? So to store the minimum, we will declare a variable, let's say ans, and we will declare it with, initialize it with some value called infinity. You can either use int max or something else, right? So initially it will be infinity, and we'll call this function, it will return some value, we'll store it in this variable, and if this value is not equals to -1, right, not equals to -1, in that case we'll take the minimum and store it in this answer. So answer is equals to minimum of answer comma value, right. Now after this for loop, we can say that this variable ans will be having the minimum number of coins that are required to get a sum of x, right. Okay, now there is a possibility, like it may happen that all the function calls can return us -1, right. And if all the function calls which we have made returns us -1, in that case we can say it is impossible to get a sum of x, right. So in that case, what will be the value of this ans? So if all the function calls are returning as -1, in that case we can say that this condition will never be true. And if this condition will never be true, in that case we can say that this ans will always be having the value of infinity, or whatever value we are providing it, right. It may be int max or something else, right. So if after this for loop ans is still equals to infinity, in that case we can say that it is impossible to get a sum of x. So we should return -1 in that case. Okay. Otherwise, we can return whatever value this ans is having, right. Cool. Now if we just look at this recursive function, then we can say that it will be having a exponential time complexity, because the first function call will make n function calls, and all those n function calls will make around n more function calls, right. So it will go exponential. If you want to discuss the exact time complexity, then we can do that in comment section, but for now we can just assume that it will be having a exponential time complexity. So let's try to see how we can optimize this problem or solution. So I have drawn a recursive tree for x equals to 5, n is equals to 2, and values of coins with 1 and 2. So we want to find out the minimum number of coins that will be required to get a sum of 5, right? In that case, if we pick a coin with value 1, then we'll call for f of 4. And if we pick a coin with value 2, in that case, we'll call for f of 3. And so on, this tree will be generated, right? Now, if we just look at this tree, can we see that there are a lot of function calls which are made again and again. For example, this f of 3. So here we want to find out the minimum number of coins that are required to get a sum of 3. Here also we want to find out the same thing. So to find out this thing, we will make a lot of function calls, right? Similarly, here also we'll make the same number of function calls. So instead of making all these calls again and again, what we can do is once we are here, once we are at this function call, we can store the minimum number of coins that are required to get a sum of 3. And when we will reach here, we can simply use that result which we have already calculated and stored, right? Simply let's say the minimum number of coins that are required to get a sum of 3 is x. So we can store this value somewhere, right? And when we will be at this function call, we can simply say that we have already calculated the minimum number of coins that are required to get a sum of 3. So we can simply return x, right? Instead of making all these function calls. Okay, cool. There is one more thing which we can observe from here is that we wanted to find out the minimum number of coins that are required to get a sum of 5. And to do so, we made a lot of recursive calls. And in all these recursive calls, we can say that the value of x is between 0 to 5. Right? Here we called for f of 5, then f of 4, f of 3, f of 3. So all these values are between 0 to 5. If we will have a negative value, then that can be handled using this if condition. Okay, cool. So if we try to generalize this thing, then we can say that to find out answer for f of x, we will be having different function calls, and all those function calls will be having value between 0 to x. So in order to memoize, we will require an array or a vector of size x plus 1, right? In this case, x is equals to 5, so we will require an array of size 6. So let's have an array. So the answer for f of 1 can be stored here, right? Answer of f of 1 can be stored here. Answer for f of 2 can be stored here. Answer of f of 3 can be stored here. And answer for f of 4 can be stored here, and answer for f of 5 can be stored here, right? So these are the only unique function calls that we have, right? Okay, so now we can have a vector, and let's call it tp, and the size of this should be x plus 1. And now we can initialize this with some value which is not possible. So we can initialize it with -2, okay? Because -2 is not a valid answer for any of the function calls, okay? Now these conditions will remain same, and here we are calculating the answer for f of x, right? So before calculating answer for f of x, we need to check. So we will have a if condition here. we need to check if we have already calculated an answer for this x or not. So if dp of x is not equals to -2, that means we have already calculated the answer for this given x. So in that case, we can return dp of x, right? Otherwise, what we'll do, we will calculate the whole answer, and before returning, we will store. So before returning, we will say dp of x will be equals to -1, and in this case, dp of x will be equals to ans, right? Cool. Now we can talk about the time and space complexity for this solution. So we can say that these two if conditions will be of order of 1, right? And this much part will be having a time complexity of order of n, right? Because we are running a loop starting from 0 to n-1. Okay, cool. Now how many times this part will be executed? So we can say it will be executed at most x number of times. Why? Because let's say we call this function for f of 1, right? And we have not calculated the answer. So in that case, it will be run n number of times. But next time when f of 1 is called, in that case, we will not run this part. We will just run this if condition, right? So for every value of x, it will be executed only once. So at most, it will be executed n number of times. So the overall time complexity will be x into n. And the space complexity for this will be order of x. So time complexity and space complexity, right? Cool. So we were able to come up with this solution, and this way of writing dp is also known as top bottom or memoization or recursive dp. There is one more way in which we can write the exact same code, and that is known as bottom top or tabulation or iterative dp. And iterative dp is a bit faster than recursive dp, because in recursive dp our code have to maintain the recursive stack, which requires some extra time and operations, right? Now we are going to write the iterative dp solutions, or we can say we are going to convert this solution into iterative dp solution. Okay, and to do so, we can try to convert this same function in a iterative dp. So let's have this same function solve, and we will pass x to this function. Okay, now first of all, we need a array or a vector of size x plus 1, so that while calculating answers, we can store those answers in that vector. So let's have a vector of size x plus 1, and we do not have to initialize it with anything, right? Okay. Now in this recursive solution, we have base cases. So we will try to handle these base cases in the iterative dp first. So we'll talk about this case later, but for now we can say when x is equals to 0, in that case the answer is 0. So we can say dp of 0 is equals to 0, right? Okay. Now we need to find out the answer for dp of 1, 2, 3, 4 and so on till x, right? So for that, what we can do, we can have a for loop starting from 1 to x, right? Now what we want to do is we want to find out the value of dp of j, and this is nothing but the minimum number of coins that are required to get a sum of j, right? Okay, so now if we just look at this recursive solution, when we wanted a sum of x, we iterated from I is equal to 0 till n-1, and we called for x minus a of I, right? So now we want a sum of j. So what we can do is we can iterate from I is equal to 0 to n-1, and we can call for j minus a of I, right? So what we can do is we can initialize a variable ans, initialized with infinity, just like we did here, right? Now what we can do is we can start iterating from I is equal to 0 till n-1, right? Now what we want is we want to find out the minimum number of coins that are required to get a sum of j minus a of I. Just like here we wanted to know the minimum number of coins that are required to get a sum of x minus a of I, right? Okay. So now j minus a of I will be smaller than j, right? And because it is smaller and we are calculating answer in increasing order of j, then we can say that for sure we must have already calculated answer for this particular value if it is greater than 0. Because if it is smaller than 0, in that case the answer is -1, and if it is greater than 0, then we must have already calculated the answer. So what we can do is, if j minus a of I is smaller than 0, in that case we can just continue, right? Or we can say that in this case the answer will be -1, and we don't want to consider that. Okay, so if this condition is not true, in that case we can say that we have a value which is greater than equals to 0, and if it is greater than equal to 0, then we must have already calculated the answer. So in that case we can say the value will be equals to dp of j minus a of I, right? Now we need to have this check. If value is not equals to -1, that means it is possible to have this sum, and in that case we can say answer is equals to minimum of answer comma value, right? Done. Just like we did here. Okay. After this for loop, we will be sure that this variable ans contains the minimum number of coins that are required to get a sum of j, right? And just like we had this check, we will also have this check here, right? If ans is equals to infinity, in that case dp of j should be equals to -1, right? Because it is impossible to get a sum of j if answer is equals to infinity. Otherwise dp of j will be equals to ans, right? Cool. So after this for loop, we will be sure that this dp array is fully updated, or we can say we know all the answers for dp of 0, dp of 1, dp of 2, and so on till dp of x, right? And we wanted to calculate the minimum number of coins that are required to get a sum of x, and dp of x represents the minimum number of coins that are required to get a sum of x, right? So this is the value which we wanted to calculate, right? So at the end we can return dp of x, right? So this will be the iterative solution. Now the time complexity of both the solutions will be same, but the only problem is that this solution is recursive in nature, and because it is recursive in nature, we will require some extra time to maintain the recursive stack, and it will be faster, and it should also get accepted on CSES. Okay. If you found the video helpful, then do like, share and subscribe. And if you are looking to improve your problem solving skills and get 100% interview ready, then take a free trial on programmingpathshala.com. Link will be in the description.